Welcome to the Horizon Audiofiles, a podcast of the Defense Horizon Journal. The Defense Horizon Journal is a professional and academic journal that features essays, reports, and analyses covering geopolitics and law, security and defense policy, peace and conflict studies, applied military science, as well as developments in weapons technology. For more information, go to www.tdhj.org.
Episode number 52. Trends and Practical Applications of Energy Storage Solutions in the Military. By Gintaras Labutis. The need for energy storage solutions. Energy is a fundamental requirement of modern military operations, affecting everything from communications and combat effectiveness to logistics and military mobility. As global security challenges grow and become more complex, militaries increasingly recognize the importance of energy and, in particular, energy resilience, the ability to sustain military operations in complex environments where traditional energy, fuel supply chains in particular, can be disrupted and can be difficult to secure. With the ever-increasing need to increase military capabilities, developing and implementing new energy storage solutions provides new opportunities for the military. Therefore, military energy plays an important role where energy storage provides additional energy efficiency and effectiveness. Currently, a variety of energy storage innovations and solutions for civilian sectors have been developed, namely, 1. Mechanical, pumped hydropower energy, compressed air energy storage, flywheels, 2. Thermal, heat storage, 3. Chemical, batteries, fuel cells, and 4. Electromagnetic, supercapacitors, superconductors, magnetic energy storage. From the military operational energy perspective, where the operational energy is required for the military to train, move, and sustain military operations, battery energy storage systems, BESS, can be considered the most feasible and desirable solution. It can be argued that the use of BESS in the military not only improves operations but also increases operational capabilities and operational resilience. BESS are currently being deployed in various areas related to operational energy, which include 1. Energy for soldiers and portable systems, communications, sensors, personal equipment. 2. Energy for small-scale autonomous equipment that may be related to the direct energy needs of soldiers, drones and other autonomous systems. 3. Energy for ground systems including military vehicles and tactical platforms. 4. Energy for forward operating bases. Furthermore, BESS are becoming a key enabler of military operational resilience, offering portable, scalable, and efficient energy storage solutions that reduce dependence on conventional fossil fuels. In recent years, significant advances in battery technology, advanced energy management, and hybrid energy solutions have led to substantial improvements in energy across all military sectors. In general terms, energy resilience is the ability to anticipate, prepare for, and adapt to changing conditions, and withstand, respond to, and recover rapidly from power disruptions. The specified requirements for maintaining the uninterrupted energy supply are related to expected energy-related disruption scenarios. For example, the U.S. Department of Defense requires military installations to be capable of sustaining an uninterrupted energy supply to maintain critical missions at the required levels of energy availability. From this resilience-related perspective, BESS solutions can effectively support critical power loads for extended periods and ensure that power outages or grid failures do not disrupt military operations. BESS are now being used to offer rapid backup power and enhanced resilience, ensuring that critical military operations can continue even under adverse conditions. Drivers affecting BESS in military applications. The growing interest in and need for further implementation of BESS in the military is driven by a range of factors, some arising from direct operational needs, while others are influenced by higher-level national policies. The key trends and drivers are discussed below. The growing need for BESS is closely linked to the military transition towards electrification worldwide, striving to mitigate and adapt to climate change. Extending the use of power energy and the electrification of military operations can be considered as one of the most visible trends. Even though traditionally military operational energy relied on the power generated from conventional diesel generators, the shift towards electric power is gaining momentum and is particularly evident in the hybrid electric and electric non-tactical military vehicles, where the advanced BESS enable them to operate efficiently across diverse terrains and missions. This trend is associated with battery energy storage applications in other operational areas, for example, for powering unmanned aerial vehicles, UAVs, or providing energy for military platforms. In general, any novel energy-related solutions must maintain or enhance operational capabilities. Efforts to improve energy resilience, especially at military bases and installations, can contribute significantly to overall military operational effectiveness. The integration of renewable energy sources is driven both by the need for higher levels of resilience and by national policies and cross-national directives aimed at supporting the energy transition. In the meantime, military forces are typically excluded from the European Union's ambitious goal of becoming the world's first climate-neutral continent by 2050, and key energy-related EU directives are not transferred to the military. However, existing examples demonstrate growing efforts to implement renewable energy generation solutions at military installations, with some systems capable of meeting up to 50% of their energy needs. There are also notable strategic-level decisions supporting the integration of renewables into military operations. It is important to note that the main driver for adopting renewable energy in military contexts is the need to reduce logistical burdens and associated risks, thereby enhancing the resilience of installations and bases. Currently, militaries are developing relatively small-scale renewable energy projects designed to better match infrastructure load profiles, particularly to lower energy demand during daytime hours. However, the integration of the use of renewable power energy into the military bases is related to intermittency and reliability risks, as mission-critical operations require a constant and uninterrupted power supply, while renewables cannot guarantee that. BESS enhance the integration of renewable energy sources, contributing to more sustainable and independent energy for military installations and bases. Renewable power generation combined with energy storage solutions can provide more reliable power, particularly in remote or off-grid locations. This shift not only ensures a continuous power supply in austere environments but also reduces the logistical burden of fuel transportation, which is often costly and vulnerable to attacks. Additionally, integration or energy storage enhances stealth capabilities by minimizing heat and noise signatures associated with traditional generators. The shift from distributed energy generation to the installation of power grids can be a feasible solution for increasing energy efficiency via optimized generation and distribution. Military installations and military bases are increasingly adopting microgrids combined with large-scale BESS. Microgrids enable installations and bases to operate more efficiently and independently from the main grid, ensuring a reliable power supply. Microgrid integration with BESS facilitates the incorporation of renewable energy sources and reduces reliance on traditional backup power systems that are usually conventional diesel generator-based. The application of smart grid technologies further optimizes energy distribution and efficiency, enabling real-time monitoring and agile and adaptive power management. Apart from the listed advantages, installing microgrids requires higher technical competencies from personnel for effective operation and maintenance. Additionally, the installation of microgrids can increase cybersecurity risks. As military energy systems become more connected and digitalized, they are increasingly vulnerable to cyber threats and electronic warfare, so energy management systems must incorporate robust cybersecurity means and protocols to prevent disruptions or hacking attempts. Given that energy is critical to operations, any compromise or failure in cybersecurity can significantly disrupt power supply, expose sensitive data, and jeopardize energy-dependent military systems and platforms. The use of BESS requires additional cybersecurity solutions, as BESS-related software solutions can be vulnerable to cyber attacks, which could lead to severe overcharging and potential explosions or microgrid integrity. Those challenges underscore the need for robust cybersecurity measures in battery management systems. It has to be noted that military dependence on foreign battery manufacturers has become a strategic concern during the last decade. This concern was particularly related to some BESS producers due to alleged links with foreign militaries. Additionally, the tensions related to critical earth materials for battery production foster the research focused on new battery technologies in line with the development of national battery strategies and execution plans. As climate change and climate-related energy security concerns grow, the military is taking a bigger role in climate change mitigation and adaptation. With the worldwide intent to lower greenhouse gas emissions, the military is increasingly turning to renewable energy sources and is implementing a variety of greenhouse gas emissions reduction solutions. Advanced BESS facilitate and enable the efficient reduction of conventional fuel use and better integration of renewable energy, thus supporting the transition from fossil fuel-based energy and reducing the overall greenhouse footprint of military operations. Ongoing research and innovations in energy storage technologies in response to the specific energy storage requirements for military operations, through improved overall battery performance, support the increasing demand of BESS. Although lithium-ion batteries remain prevalent due to their high energy density and efficiency, emerging technologies offer potential enhancements in energy density, energy capacity, longer lifespans, battery safety, and overall operational reliability. The key focus for military BESS is related to energy density, battery durability, and performance in extreme conditions such as harsh climates, extreme temperatures, and rough handling. When analyzing military energy storage needs, it can be concluded that military operational environments pose unique challenges to energy storage that do not allow the direct use of commercial off-the-shelf solutions. However, the required battery energy density versus battery weight remains crucial for most military operational energy requirements. Selected operational energy areas for BESS applications. BESS solutions are generally applicable across all major military branches, land, air, and naval, with domain-specific requirements for each platform. However, certain needs are common across all branches and should be highlighted. Energy requirements, for soldiers, platforms, and bases, universally relevant and strategically managed across all branches of the military. From this perspective, the present analysis will focus on BESS solutions for soldiers, tactical and non-tactical vehicles, and BESS for military bases. Soldier energy. Soldier operational capabilities are directly associated with energy use. Soldiers rely on large amounts of information and communication systems, including communication devices, sensors, night vision equipment, targeting systems, and others. In some scenarios, the energy for the UAVs is considered part of the soldier's energy as well. Soldier portable electronic systems require lightweight, high energy capacity and durable battery solutions to ensure uninterrupted operation in a combat environment. Improvements in energy storage technologies can reduce the weight of a battery for a given amount of energy or obtain more energy from the same battery weight. This means that the desired balance of required energy, meaning more energy, and battery weight, meaning less weight, must be achieved. It is estimated that the weight of portable batteries for a dismounted soldier can reach up to 5 kilograms, and in some cases, even exceed this estimate depending on mission requirements and equipment load. However, soldier energy consumption can be reduced by using advanced power management solutions or by reducing the number of different types of batteries. It is also important to meet the requirements for interoperability with other equipment. The pairing of batteries with solar renewables will extend soldiers' operational effectiveness. It has to be mentioned that the exact solar energy requirements depend on specific mission scenarios. Efforts to reduce this weight include developing lighter, more energy-dense batteries, centralized power systems, and alternative energy sources such as solar panels and rechargeable systems. However, the need for reliable power remains critical, making battery weight a persistent challenge for modern militaries. With regard to BESS, noteworthy innovations in BESS solutions include lightweight, flexible batteries that can be integrated into armor and helmets. Additionally, modular battery packs, which are interchangeable and capable of powering multiple devices while being easily recharged, are significant advancements. Smart battery management systems, which prevent overcharging and continuously monitor battery status, are also crucial developments. Beyond the use of solar energy for battery charging, research and development are investigating additional energy generation methods, such as harnessing power from a soldier's movement or body heat. All those needs will extend the mission duration of a dismounted soldier in extreme conditions, even without constant and reliable access to a power source. It also has to be noted that despite the variety of solutions, the advantages of the increase in battery energy density are the main focus for innovations. Energy for land platforms. Traditionally, land platforms include a variety of functionalities to support and protect soldiers on the battlefield, including combat vehicles, remote-controlled equipment, targeting systems, and missiles. In addition to energy density and weight, the specific mission-related energy storage parameters are important for land platforms. Usually, BESS require a wider temperature range and additional mechanical features related to increased shocks and vibration. Presently used lithium-ion batteries operate within a relatively narrow temperature range. However, the optimal operating range, especially for charging, is even more limited, necessitating additional thermal management solutions, heating or cooling, to maintain battery performance and longevity in BESS applications. Tactical vehicles provide a range of combat, logistics, and mobility functions, while non-tactical vehicles can provide support in areas that are not directly affected by combat scenarios. Traditionally, the propulsion of military vehicles relied on liquid fuels. The present trend towards electrification of non-tactical vehicles, both for hybrid and electric options, reduces the reliance on conventional fuels. The increasing number of hybrid non-tactical vehicles indicates the ease of transition from fuel-based vehicles to hybrids or electric. The implementation of innovations related to hybrid solutions for tactical vehicle propulsion is limited to the demands for energy density. However, both tactical and non-tactical vehicles can provide additional onboard power for powering advanced equipment specific to military uses, e.g., weapon systems, communications, sensors. The ability for silent operations and reduced thermal signatures can be considered as the other important feature, as internal combustion engines produce significant noise and heat, making military vehicles and personnel more detectable. In contrast, battery-powered vehicles and equipment operate silently and with lower thermal emissions, improving stealth and survivability. The advantages of BESS can also provide longer endurance for unmanned systems such as drones, UAVs, and autonomous ground vehicles, UGVs, that rely on high-density battery storage for extended mission durations, increasing the operational range and mission capabilities of these systems. From the considerations mentioned above, it has to be stated that BESS solutions for land platforms systems support the enhancement of military capabilities and open new capability options for the military. Energy for forward operating bases. Military forward operating bases, FOBs, require a secure, uninterrupted energy supply to power the functioning of command and control units, surveillance and force protection systems, other operational facilities, including food processing, water and sewage systems, and other quality of life, (QoL) related systems. FOBs usually consist of temporary, tents, or semi-permanent structures with basic or extended services. In most cases, the energy supply for FOBs relies on fuel generators combined with energy supply from external power grids. For advanced FOBs, internal microgrid solutions can be provided. Small-scale FOBs, such as combat outposts, COPs, or forward operating sites, FOS, can represent infrastructure with basic shelter solutions and other limited facilities, such as small-scale command and control center, water storage, and other limited facilities, when conventional fuel generators usually provide the limited power supply. Diesel generators. Traditionally employed at FOBs and COPs, are inefficient, noisy, and vulnerable to attacks. In contrast, BESS solutions can optimize fuel use during periods of low energy demand and enhance the overall efficiency of generators. The integration of batteries with diesel generators enhances fuel efficiency and reduces fuel consumption. This is achieved through several mechanisms. The load leveling allows batteries to manage fluctuating power demands, enabling generators to operate at optimal efficiency rather than idling or running at low loads, which is both inefficient and harmful to the equipment. The BESS help reduce generator idle time by supplying power during low load periods, allowing the generator to be turned off entirely. By decreasing generator runtime, fuel consumption is conserved, which is especially critical in remote or hostile environments where resupply is difficult. Additionally, batteries provide reliable backup power for mission-critical systems, ensuring uninterrupted command and control operations during power failures. They also maintain operational continuity during grid outages or cyber attacks. And finally, the reliance on batteries reduces the vulnerability of fuel supply lines, minimizing the risks associated with fuel transportation disruptions. BESS solutions for FOBs and COPs provide additional capabilities to use existing generators with the possibility to integrate alternative energy solutions, particularly photovoltaic, PV, systems. At the same time, the wind power is limited due to terrain specifics related to military base protection, radar functioning, or technical and engineering requirements. However, PV solutions require good power management systems to integrate with existing energy systems successfully and efficiently. In this respect, the BESS facilitate the integration of PV and play a substantial role in reducing fuel demands. Battery storage combined with renewable sources allows FOBs to operate independently for longer durations. In general, FOBs and COPs experience logistical challenges of delivering fuel, so the most direct application of energy storage is to support the existing infrastructure in ways that reduce overall fuel use. The additional viable solution is related to microgrid solutions for the base as the integrated system of energy generating, energy storage, and energy controls and energy management system to optimize generating capacity and to adjust the power generation as loads increase or decrease. Microgrid technologies also incorporate automated control technologies and aggregate load demand from multiple sources to meet the system's current and expected power demands most efficiently. During the structured interviews with military energy users, it was concluded that BESS for FOBs or other deployed force infrastructure can be considered as the key priority area for efficient military energy use and demands for energy resilience. Military operations require rapid deployment of energy solutions that can be scaled according to the mission's needs. Modular systems can be integrated with renewables, solar, wind, hybrid systems, or traditional generators for optimized performance. Modular and scalable battery storage systems, battery packs, allow for flexible energy provision across various operations, from small reconnaissance missions to large-scale combat operations. It is worth noting that NATO's current flagship energy security research project focuses on energy monitoring, metering, and optimization in deployed camps and the battlefield, with Ukraine among the participating members. Existing BESS technologies solutions for military and ongoing innovations in BESS. As the military seeks more efficient, reliable, and resilient energy storage solutions, various battery technologies are being integrated into the military. Each technology offers unique advantages and challenges, depending on the specific operational requirements, such as mobility, durability, energy density, and rechargeability. Presently, the following battery storage technologies are in use, with ongoing development specifically tailored for military applications. These include lithium-ion batteries with further improvements and modifications, solid-state batteries, SSB, ion-based batteries, such as ion flow or ion-air batteries, and metal-air batteries. Li-ion batteries have become the dominant energy storage technology in both civilian and military applications due to their high energy density and rechargeability. Li-ion batteries offer several advantages. They provide high energy density, which translates into long-lasting power for mission-critical equipment. They are rechargeable and scalable, making them suitable for a wide range of applications, from handheld radios to electric combat vehicles. Moreover, they are mature and commercially available, supported by well-developed supply chains and large-scale global production. Despite their widespread military applications, Li-ion battery energy storage systems, BESS, face several limitations and challenges. These include thermal runaway and safety risks, as Li-ion batteries are prone to overheating, fire, and explosion under extreme conditions. Additionally, they have a limited lifespan, with performance degrading over time. Another critical concern is the vulnerability of the supply chain, as key raw materials such as lithium, cobalt, and nickel are primarily extracted in geopolitically sensitive regions, posing risks to secure and stable procurement. Despite the existing limitations of Li-ion BESS, lithium-ion batteries continue to dominate most applications, with major efforts focused on mitigating their disadvantages. To reduce supply chain vulnerabilities, sodium-ion batteries have emerged as a result of efforts to replace lithium with more abundant and less critical elements, such as sodium. Solid-state batteries, SSBs, represent the next generation of battery technology, addressing many of the safety and performance limitations associated with traditional lithium-ion batteries. Unlike conventional designs that rely on liquid electrolytes, SSBs use solid electrolytes, which improve stability, energy density, and longevity. SSBs offer several key advantages. They provide higher energy density, enabling greater energy storage compared to traditional lithium-ion batteries. Their use of solid electrolytes significantly enhances safety by eliminating the fire risks linked to thermal runaway. In addition, SSBs demonstrate improved durability, being more resistant to temperature fluctuations and physical damage. They also offer a longer lifespan, with minimal degradation over repeated charge cycles. Furthermore, SSBs currently exhibit slower charge and discharge rates compared to lithium-ion batteries. Nevertheless, the future outlook for SSBs in military applications is promising, and it is expected that the wide-scale production of SSBs will start in 2026. Their potential is particularly strong in areas such as soldier systems that require lightweight, high-capacity energy storage, long-endurance unmanned aerial vehicles, and resilient forward operating base (FOB) energy grids that demand lower failure rates and safer operation. It is also worth mentioning the NATO SPS project focused on the development of thin-film SSBs with efficient, stable, and safe performance in low-temperature environments. The project aims to address key issues associated with liquid electrolytes, including high-temperature swelling, leakage under external pressure, and ignition risks. Flow batteries are designed for long-duration energy storage, making them particularly well-suited for military bases, command centers, and microgrid solutions. Unlike traditional batteries, they store energy in liquid electrolytes that circulate through electrochemical cells, allowing for efficient and sustained energy delivery. These batteries offer several advantages for military applications. They have a long operational lifespan, often exceeding 20 years with minimal degradation. Their storage capacity is easily scalable by expanding the size of the electrolyte tanks, making them adaptable to various energy demands. Additionally, flow batteries support rapid charging and allow deep discharging without compromising performance, which makes them well-suited for continuous power supply in microgrid setups. However, flow batteries also present several limitations and challenges. Their relatively low energy density makes them unsuitable for portable applications such as soldier systems or military vehicles. They are also heavy and large in size, which limits mobility and deployment flexibility. Furthermore, their maintenance is more complex due to the intricate systems required for electrolyte circulation. Despite these challenges, flow batteries hold strong potential in military use cases, particularly for large-scale energy storage at bases and forward operating positions, as well as for integration with renewable energy sources like solar and wind. Metal-air batteries, such as aluminium-air, zinc-air, and lithium-air variants, currently offer the highest energy densities of any battery technology. These batteries are exceptionally lightweight, making them highly attractive for military applications with critical weight and energy capacity. The key advantages of metal-air batteries include their extremely high energy density and ability to store up to 10 times more energy than conventional lithium-ion batteries. Their lightweight nature enhances portability, which is especially important for long-range missions. Additionally, metal-air batteries have an extended shelf life, remaining operational over long periods without significant degradation. However, these batteries also face notable limitations. They typically have a slow discharge rate, making them unsuitable for applications that require high power output or rapid energy delivery. Corrosion and stability issues also pose technical challenges, particularly in harsh or variable environments. Despite these drawbacks, metal-air batteries hold strong potential in specific military use cases. The current NATO SPS research project, High-Energy Calcium-Oxygen Batteries, focuses on the development of advanced calcium-oxygen batteries as a promising alternative to lithium-ion technology. The project aims to develop a rechargeable battery with high energy density. These innovations strive to establish efficient and widely adoptable post-lithium technologies, addressing both the environmental impact of lithium extraction and potential future supply shortages. It should be noted that the selected types of BESS do not represent the full range of technologies successfully used in the military, rather, they highlight some of the most commonly used or potentially most applicable solutions. In addition to existing and adapted solutions, some promising technological innovations are emerging, with potential final adaptation for military applications, such as lithium-sulfur batteries, which provide high energy density and are considered promising alternatives to lithium-ion batteries, particularly for applications that prioritize lightweight design and long endurance, such as wearable electronics and small UAVs. Graphene-based batteries are recognized for their lightweight structure, rapid charging capabilities, and high energy density. These attributes make them particularly well-suited for high-performance military applications, including soldier-worn power systems, electric and hybrid vehicles, and other portable energy sources. It has to be noted that the developments in nanotechnology are opening new research and development opportunities for BESS. In alignment with the military's shift toward more sustainable energy practices, there is an increasing focus on battery end-of-life management. Key priorities include recycling, safe disposal, and the development of environmentally friendly materials. Future battery technologies will be designed for easier recycling, minimizing waste, and reducing dependence on raw material extraction. Ongoing research into biodegradable and recyclable materials aims to make military energy storage solutions more sustainable and eco-friendly. The integration of artificial intelligence with BESS is poised to revolutionize military energy management. AI technologies will predict energy demand, optimize charging cycles, and help prevent energy shortages. Intelligent energy management platforms will dynamically allocate power across portable systems, vehicles, and installations, improving efficiency in complex operational environments. Additionally, AI-driven systems will automate charging schedules and optimize energy distribution, reducing downtime and ensuring continuous power availability across military assets. It is also expected that through the AI applications, the BESS research will receive additional means for new battery chemistry-related solutions. Based on this review of ongoing research on BESS, one can conclude that there are focused efforts in research and innovation. It should be noted that the scope of BESS research and innovations encompasses a wide variety of options. Recent European Defence Fund, EDF, calls also highlight the urgent need for improved energy management at military bases, emphasizing the development of novel energy storage solutions, specifically, next-generation electrical energy storage for military forward operating bases and energy-independent, efficient systems for military camps. Discussion and conclusions. The analysis of military needs for battery energy storage systems, BESS, and the existing solutions indicates that the demand for advanced energy storage is growing as modern and future defense capabilities require increasing amounts of energy. This trend is particularly evident in the energy storage needs of unmounted soldiers. For land platforms and expeditionary military bases, the operational use of BESS is largely limited to traditional solutions. Military-related energy and energy-related resilience for the military can be substantially enhanced with broader BESS implementation. In many critical cases, energy storage solutions are effectively integrated into military energy infrastructures, although they are not fully recognized in many scenarios. Examining current BESS demonstrates that these solutions are already in use, mostly on a small scale. BESS can be further integrated, provided military capability development institutions and units establish clear operational requirements. It is important to note that the operational requirements for BESS vary and must be tailored to specific mission needs without compromising overall capabilities. The formulation of BESS-related operational requirements is closely tied to a policy-level strategic approach that integrates BESS solutions as a component of energy resilience. These requirements, driven by energy demands and potential disruption scenarios, should be defined not at the individual military unit level but at the broader energy policy and strategic planning level. From this perspective, energy storage solutions will improve energy efficiency and significantly enhance energy resilience. As research continues to yield more feasible BESS options, these systems are expected to be deployed on a wider scale across military systems and units. The evolving energy requirements for specific operational areas underscore the growing need for BESS, provided that these solutions meet the strict demands of military applications. Present requirements for BESS also highlight the need for continued battery storage innovation, which can be achieved through collaborative multinational research efforts supported by public financing. Author, Gintaras Labutis, Ph.D., MBA, Research Interests, Military Management, Sustainable Energy Management, Energy for Security and Defense, Pro-Environmental Behavior in the Military, the Resilience of Critical Energy Infrastructures, Energy-Related Technologies, and Applications. The views contained in this article are the author's own and do not represent the views of the Military Academy of Lithuania.
This was the Horizon Audiofiles, a podcast of the Defense Horizon Journal. For more information, go to www.tdhj.org. Thank you for listening.